So let's continue with our previous discussion on Bootstrap. So in the last lecture, we talked about the general formulation of Bootstrap. In particular, we explained Bootstrap as this two-stage process. So the two-stage means that we first would like to estimate a performance measure or performance metric for an estimator. And we denote that by lambda NF. So basically, this is a performance measure. So one thing you should think about is, why do we have the subscript n? The n actually comes from the sample size and it's involved in our estimator. So as we are evaluating an estimator's performance, then the estimator's sample size or estimator, we call that, let me put here, we call theta hat n. This estimator itself depends on n, so that's why n should also be in the performance measure. But please note that one thing is this performance measure, although it depends on the sample size, it's not random, it's fixed. So this is to know, is fixed. Because you can think about examples like the CDF value of this root n theta hat n minus theta, like the CDF of this distribution at a given value, right? The left-tail probability, or the bias, which is expectation of theta hat n minus theta, or the variance. These three things are the three most commonly used performance measures of an estimator. And all these performance measures depend on the true distribution F. That is the distribution where the sample comes from, and theta hat n is based on that sample. So that's why F is the true distribution here, and lambda n is the performance measure which indicates the sample size. So these are the examples. But as we said, these are unknown quantities because they depend on the true distribution F. What do? So Bootstrap is leveraging this idea, which we describe in general, which we described for the previous case as general abstraction called statistical functional. That is, we consider an estimator, or we consider the parameter. We consider the parameter theta as a functional of the true distribution F, and we consider theta hat n as a plugin of this functional by replacing F with F and hat, right? F and hat is the empirical CDF. So this is how we can derive an estimator in the general sense, plug in. And now we're leveraging this idea to estimate the performance measure. So that's why if the performance measure can be expressed as a functional of the CDF, then we can still replace F by F and hat, and then we get an estimator. So this is the underlying idea behind Bootstrap. That is, we use the empirical CDF to construct an estimator for the performance measure of an estimator. Okay. All right, so we're talking about this estimator theta hat n as our evaluation target, but to estimate its performance, we come up with another estimator. Okay, the second stage is an approximation. So we have shown you example that if you want to calculate this exact plugin estimator, you may have to enumerate all possibilities of your sample by sampling with replacement, right? So essentially, you need to sample, so you need to create a hypothetical sample from your actual sample, because your actual sample represents F and hat, empirical distribution, so which is an n value discrete distribution. Each value in your sample has probability mass 1 over n, right? So if you sample from there, then you have how many possibilities? If you want to get a hypothetical sample of size n, then sample with replacement means that you have n to the n possibilities, right? So that's a That's a phenomenal number. So a large number, atomic number. So what do? You are approximating this by Monte Carlo. That is, I'm not going through all possible samples. I just get a large number of a large enough number of samples, then I calculate the average. So as an approximation of the true estimator. So the second stage is the approximation. So that's why for Bootstrap, essentially, we often set the number of Bootstrap samples to be a large enough number, such as 1,000. Then we are actually computing this. So in this case, B, if we set it to 1,000, then B is considered to be large enough, and you hope that this is a good enough Monte Carlo approximation of this. And so what I want to emphasize here is what you can control is the second stage. You can set this B to be large enough so you have a very good approximation of this estimator. But what you cannot control is the first stage. Whether this plugin estimator is a good estimator or not, that depends on the distribution. Yeah, so that depends on distribution and also the performance measure you're calculating. Okay. All right, so let's continue from here. Let's continue our reading from here. The method is in fact much more general, with many alternatives being available for each of the stages, 2 stages. Regarding the first stage, depending on the situation, quite different estimators may be used to estimate this performance measure. The following example provides just one illustration. So the key thing is, how do you obtain this F and hat? So we can say that using the empirical CDF, we are using a so-called non-parametric version, unparametric estimator of F, because we're just using empirical CDF without making any assumptions. But what if you have some knowledge or some confidence in your knowledge about the distribution F? For example, you think it's reasonable to assume it to be a Gaussian distribution, then why cannot we just use our estimated Gaussian distribution as F and hat instead of using the empirical CDF, right? So this is what we call the parametric bootstrap. So for parametric bootstrap, the difference is that your F and hat is a parametric estimator of F. That's it. So you use a parametric version to estimate this true CDF. Okay, let's read this example. The parametric bootstrap. Suppose that we are estimating the median parameter theta of F by the sample median, so the middle point of your sample, and wish to estimate the error probability. So this is what we said, right? So you calculate this error scaled by n, so it stabilizes. It has a finite variance, not deteriorating as n increases. So you're as interested in this CDF, so the error distribution is left tail probability. So this is what I call the example 1 for this performance metric measure. Okay, so if nothing's known about the F, which is required to calculate this probability, we could do the plugin. That is, F becomes F and hat, theta hat n becomes theta hat n star. Based on the hypothetical sample, theta becomes theta hat n, right? Theta is the population F distribution, true distribution's median. Theta hat n is the sample's median. And now we are treating the sample empirical CDF as a plug-in estimator for the true F. So that's why theta becomes theta hat n. Okay, and so how do you calculate this theta hat n star? You will use a hypothetical sample, which is sampled with replacement from your empirical CDF, the actual sample. Suppose, however, that it is known that x1 to xm is a sample from a Cauchy distribution. So this is what I just said. You have some knowledge about the distribution's shape or family, Cauchy distribution. Cauchy has 2 parameters, a center parameter and a scale parameter. Please note that for Cauchy, it doesn't have any moments, like the mean, variance, you don't have that, but it's too heavy-tailed. So we only talk about its center and scale. We might then still use theta hat n, the sample median, to estimate theta the median. However, instead of estimating this 19.1 by this 19.2, which is the non-parametric version, what you can do, you might prefer to estimate it in the parametric way. So in this case, your hypothetical sample is now sampled from the fitted Cauchy distribution instead of sample from the sample x1 to xm. So, and you're still doing the sampling, but now this distribution you sample from is no longer an n-value discrete distribution, but it is a Cauchy distribution. It's just that its parameters are estimated from your actual sample. And this is called parametric bootstrap. Okay, then the Cauchy distribution center at theta hat n with a scale parameter bn, which is a consistent estimator. For example, you can use the MLE of beta, b. This estimator utilizes the Cauchy structure of f. And this is something we didn't actually use in our non-parametric bootstrap. You just use x1 to xn without having any assumptions about the underlying distribution. Then at the second stage, you will use this estimator instead of the previous one. So we use double star to indicate that here the hypothetical sample is sampled from the parametric distribution. That's it. Okay. It then be approximated by bootstrap sample from the Cauchy distribution with the parameter estimates. Okay, that's called parametric bootstrap. And there are some discussion regarding which one is better. But in general, the intuition is that you would prefer to use the parametric distribution if you think your distribution assumption, such as Cauchy distribution, is reasonable. Because basically you're adding more information, right? You're not just using the sample alone. Let us now return to the general case. Alternatives are available not only for the first stage of the process, how to come up with f and hat, but also for stage 2. In particular, bootstrap samples may be obtained by resampling plans other than simple resampling, because we only talk about simple resampling. A variety of such plans. You can Google these things, right? For example, antithetic, balance, and importance sampling. So these are people's invention of sampling techniques. So the general idea is that you can sample less, but to obtain more stability in your results. For example, if you want to do simple bootstrap, you just do rate independent sampling for capital B, say 1,000 times. But if you don't have the computational budget, you may use these ways to save your B, to make B smaller. Yeah. Okay, this is bootstrap literature together with indications of the type of problems for which each is appropriate. We will conclude with a fairly brief discussion of some theoretical properties of the plugin estimator. So this is the one we intend to have in stage 1, such as consistency, asymptotic normality, and comparison with more traditional estimators. These problems concern only the behavior of the estimator itself, not that of the approximation, which is quite separate and presents little difficulty. So essentially, for now on, I want to say that when we say bootstrap or bootstrap theory, we talk about this. We talk about this plugin estimator, whether it is a good estimator or not. Because for the second stage, the approximation, Monte Carlo approximation, we know it can work pretty well as long as B is large, right? So that's not our concern. That's in our control. But this property, whether the plugin estimator is something good and reliable to use, that is out of our control, and we must know that. So like that. So when people say bootstrap works or not, they're talking about properties about this estimator. Okay. In much of the bootstrap literature, the bootstrap is said to work if this plugin estimator is consistent for estimating this performance measure of your interest in the sense that their difference converge to 0 in probability. So why, I have 2 questions for you to think about. First of all, why do we have lambda NF on the left-hand side, not on the right-hand side? Why didn't we write this? Mathematical notation wise, why don't we write it this way? The reason is we shouldn't have n on the right-hand side. Right-hand side is the limit, right? It shouldn't involve n. Yeah, that's the thing. Yeah. Okay. So second of all, in these two terms in the difference, which one is random? Left one. This one is random. Yeah. I want to emphasize the importance of understanding randomness. This is fixed, right? So I just said this is fixed because it's a performance measure of an estimator, even though the estimator is random, but the measure is fixed, right? Like bias, variance is fixed. Okay, but the left-hand side is an estimator. Estimator is always random because it depends on our sample. So that's why the difference is random. And for such a random quantity to say it converges to zero, we must specify the mode. And that's what we said in the first two classes, 4 modes of convergence. And here we think we define it to be the convergence in probability. Okay. And before taking up the question of consistency, it is useful to note that typically the sequence lambda n performance measure, which depends on the sample size, will tend to a limit lambda. So this is something we usually have for the performance measure. And please note that this has nothing to do with our plug-in estimator. It's just the measure itself. For example, the error probability, the bias, the variance, they may all tend to a limit asymptotically, not depending on m. Okay, let's look at the examples. For all f's under consideration. For example, if this is the error probability, then it depends on the distribution of this. Root n times the theta m estimator minus tf, which is theta, right? So this has a limiting distribution. For example, central limit theorem give us the limiting distribution as Gaussian. Then in this case, if you have a limiting distribution as Gaussian, then clearly this error probability will have a limit. And the limit is the CDF value under the limiting Gaussian distribution, right? You basically replace this by a random variable following that limiting Gaussian distribution. And that probability is what you get. So this is following exactly the definition of convergence in law, because convergence in law indicates convergence of CDF function, right? So you know this as a limit. And the limit doesn't carry n because the limiting Gaussian distribution doesn't carry n. Okay, if this lambda and f is not an error probability, but the bias of an estimator or the variance of an estimator, then we know that in many cases, the bias will go down to 0 as n goes to infinity. That's called asymptotically unbiased. So that's why here this would maybe 0. Or if it's the variance, if lambda and f is the variance may also stabilize, right? May converge to the asymptotic variance. So these are the cases where the performance measure itself converges, right? And the convergence will no longer depend, the limit will no longer depend on sample size n. All right, so if we have this property, that is, the performance measure of theta at n has its own limit, then the desired consistency of the plug-in estimator can actually be equivalent to that the plug-in estimator converging probability to the limit of the performance measure. Okay, so it's like this thing. So basically, there are 3 things. The performance measure depends on n. The estimator of the performance measure random. We previously want to show that their difference go to 0 in probability. But since the performance measure itself has a limit, then we can just directly show that to get the consistency of the plug-in estimator, we just need to show the plug-in estimator convergence in probability to the limit of the performance measure. And just as here, I said we cannot write it this way because the right-hand side cannot carry n. But now I don't have this problem because the limit doesn't depend on n. Okay, and the proof is just one line, actually. It's just that we want to show this difference between plug-in estimator and performance measure. The difference go down to 0 in probability. We show their difference. It can be written in 2 parts. That is, it's the plug-in estimator and the limiting performance measure, and the difference between the finite n performance measure and the limit. right? So by decomposing these two parts, so that's why we can say that this converge to zero in probability is equivalent to this converge to zero in probability, because we know this part always converge. And you see here, for this convergence of the performance measure, we don't need to specify the mode since it's not random. Lambda and F is not random. So that's why we just say it's convergent. Okay, so essentially we're saying that to show that the plugin estimator, or we can call Bootstrap, right? Bootstrap plugin estimator is consistent. We can skip the performance measure for some finite m. We directly target its limit. For example, if you show this performance measure as a bias, if we know the bias is asymptotically zero, then what we can do is that we just show, okay, the plugin estimator converges to zero in probability. Then we don't need to worry about what is the finite sample bias, because that formula may be complicated. Does that make sense? Yeah. Okay, so that's the thing. Let's continue. This lemma reduces the generalized consistency definition, which is this: difference converge to zero probability, to the standard definition of convergence in probability of the estimator to a constant. Proving consistency in the present setting tends to be difficult because typically no explicit expression is available for the plugin estimator, which instead express conditionally in terms of the hypothetical variables, right? We enumerate all the hypothetical samples. The following example, which illustrates both situations in which lambda and fn hat is and is not consistent, is an exception. Here, lambda fn can be expressed directly in terms of the x's. Okay, so here we have a good form for this expression. Now let's look at this. So I think I may want to change this to, let me see. Yeah, I think I would change this to be variance. That's something I want to do. Variance under f of this, change it to this. So it's basically the variance of the estimator, but I scale the estimator by root n. So I will want to make sure this variance is not going down to zero. That's it. Okay. Theta and hat is a U, so we can actually come up with using the U statistic to give us an unbiased estimator of theta. This is what we covered in previous lectures. So using the U statistic as the estimator, this is the formula. And choose two. And then we consider two unequal, right, not identical values in our sample, xi, xj. I must not be equal to j. So we have shown previously, this is the variance formula for U statistic. Since here, our U statistic or define the functional we use is just defined depending on two hypothetical samples, right? So a sample size 2, a hypothetical sample size 2. So that's why the U statistics variance only has two terms, sigma 1 squared, sigma 2 squared. And if you remember what this is based on that so-called H projection. The sigma 1 squared is that we're calculating the covariance of the G function where x1 and x2 and x and x3, they share the x1 and they differ in the second entry, right? This x2 and x3 are independent. This is how we define sigma 1 squared. And for sigma 2 squared, is defined as the covariance where the G functions, both entries are identical. So it's G x1, G x1, x2. So both are identical. And then this covariance is exactly the variance, right? Because they're identical. So we're basically expressing sigma 1 squared, sigma 2 squared based on the covariance and variance formula. So for covariance, we know it's equal to the expectation of the product minus the product of expectations. And for the variance formula, we know it's equal to the expectation of the square minus the square of expectation, right? We're using this formula again. So essentially, your lambda and f, which is variance of sigma hat n times root n. Essentially, you need to multiply the square of root n outside of the variance. So you're multiplying n to this term, to this variance of un. So multiplying n, you basically cancel n in each term from the denominator. This gives me lambda f, right? Performance measure. So now you see for these two terms. And as we know already, the first term dominates in order because when you let n go to infinity, you are left with 4 times sigma 1 squared. The second term goes to 0, right? So this is our limit. So that's why here we have shown that in this case, lambda and f, the performance measure, does have a limit which no longer depends on n. Yeah. Then, how about the plug-in estimator consistency? So plug-in estimator will plug in the performance measure by changing f to f and hat. So correspondingly, sigma 1 squared becomes sigma 1 star squared. Sigma 2 squared becomes sigma 2 star squared. So by adding star, we mean that we're calculating sigma 1 squared, sigma 2 squared based on a hypothetical sample. That's it, right? And based on the empirical distribution, not the true distribution. So in this case, when we change, sigma 1 squared is a covariance, and the covariance is under F. And based on x1, x2, x3 independently IID from F. Now we change it to sigma 1 star squared to be covariance under F and hat, empirical CDF. Now x1 star, x2 star, x3 star are hypothetical samples from F and hat. Okay, and similarly for sigma 2 squared. Okay, so, because it's based on f and hat, we can use our exact sample of x1 to xn to do the exact calculation. So again, it's the expectation of the product minus product expectations. So as here, by averaging, we need to enumerate all possibilities of x1 star, x2 star, x3 star. They can be sample with replacement from my x1 to xn. So that's why each can be x1 to xn, right? I go through all of them, and there are how many pair, how many triplets, n cube triplets. I take the average of that. And this is the average of the product. And for the second part is the square of the average, right? Basically, for each average, now I only go through a pair, xi, xj, both can go from 1 to n. So that's my exact formula for sigma 1 star square. Similarly, I can get exact formula for sigma 2 star square based on my sample. However, the question is, do you think this plug-in estimator is consistent for estimating lambda and f? So essentially, comparing the two things, this is the lambda and f, which depends on sigma 1 squared, sigma 2 squared. This is lambda and f and hat, which depends on sigma 1 star squared, sigma 2 star squared, right? So for these two things, the question is whether this sigma 1 star squared is the consistent estimate for sigma 1 squared, whether sigma 2 star squared is a consistent estimate for that. And here the challenge is that, again, just like in the V statistic, we now have replicates. So it's possible that xi, xj, or xi, xk, they are identical, right? We don't exclude the replicates. If they're identical, then that term itself should not be meaningful. That term is not useful for estimating that sigma 1 squared, sigma 2. Yeah, so that's the thing. But if such replicates are the minority, they don't dominate this average, then that could be fine. So essentially having them there doesn't change the asymptotic, which is a behavior, the consistency of this, because these identical terms are minority. So this is the argument here. So that lambda and f and hat may not be consistent for estimating lambda and f is a consequence of the fact that un and hence sigma 1 squared, sigma 2 squared, lambda and f depend on only on g x I x j for I doesn't equal to j, while sigma 1 star square and sigma 2 star square and hence lambda and f and hat depend also on GXIXI, you could have identical things sampled. The difficulty does not arise, however, when sigma 1 squared, sigma 2 squared, and this quantity, the variance of this GXIXI, we just give a notation gamma squared, when they're all finite. So if they're all finite, like I said, finite means that it don't dominate a term, especially gamma squared don't dominate a term, then we still have that sigma 1 star square being consistent for sigma 1 square, and sigma 2 star square being consistent for sigma 2 square. So just like the GXIXI terms don't dominate. Yeah, so if that's the case, then we can still have this consistency we desire. However, if this identical GXIXI term has infinite variance, then this whole thing breaks down, right? So you cannot ignore that term, essentially. That's the intuition. So basically, when you see the biggest challenge for Bootstrap is that you may have the sample with replacement issue. Yeah, because but essentially you cannot do anything for it because the original data sampling procedure from F to get X1 to Xm, you're actually doing sample with replacement, right? Sampling itself is with replacement. It's just that if F is continuous, then you wouldn't have identical values. But now you're using a discrete sample to represent like a continuous F, then that kind of discrepancy is always there. Okay, so let's continue here. Okay, so coming back to this lemma and to get this showing that if you have the performance measure converge to a limit, you just need to show the plugin estimator converge to the same limit in probability, just to show the plugin is consistent. Okay, and this comment is very important. Consistency typically holds, but cannot be taken for granted. A good summary of both the theory and some of the principal examples can be found in chapter 3 of this book. It's a very good book for Bootstrap. It's called Sean Tu's book, Jackknife and Bootstrap, 1995. A key technique is the Berry-Essen theorem, which gives an upper bound on the maximal error of approximation in Kolmogorov-Smirnov distance between the true distribution of the scale sample mean and the normal distribution. This is something I previously skipped in our lecture, but I would like to make it back so we can look at the Berry-Essen theorem together. And this is a good case to talk about it because now we have this concrete application of it in Bootstrap. So let me retrieve this part. Okay, so this is actually, we should have talked about it after we introduced the central limit theorem, but that time we skipped this part. So what is the Berry-Essen theorem? It's actually talking about how well is our actual error distribution from the limiting distribution, which is normal distribution given by the central limit theorem. That's the question. All right, so let's look at the statement. Let yi be the scaled version of xi, or normalized version of xi. It's xi minus mu over sigma squared. So by doing so, we can basically assume that yi has mean 0 and variance 1. That will make the discussion simpler. So, and let Tn be the root n of yn bar. So this is what we have on the left of the central limit theorem, right? Basically, it should be yi minus its mean. And since its mean is just 0, so now it should be yn bar minus the mean, 0. So we just have that. So essentially, the central limit theorem tells us Tn converges in law to standard normal, and this is the CLT result. Now the Berry-Essen theorem is giving us the distribution of the distance between the CLT's limit, standard normal, and Tn's actual distribution. What is their distance? Okay, let G and X denote the CDF, cumulative function of Tn. So no, this notation, okay. CDF function at X. That is the probability of Tn less or equal than X. Then the CLT states that for any X, yeah, So G and X converges to phi X. Phi is the CDF of standard normal for any X, right? This is exactly the definition of convergence law. That is the point-wise convergence of the CDF function. Yeah, and since phi is bounded and continuous, the convergence is uniform. Yeah, this is also something we know before. And from pointwise convergence to the uniform convergence, which is a real analysis result, right? So essentially, if the limiting function is bounded, because the standard normal CDF or any CDF is bounded between 0 and 1, and it's always continuous everywhere, right? So that's why the uniform continuity, we can have that. So the sup of x of this difference is converging to 0 as n goes to infinity. But this limit result says nothing about how close the left and right hand side must be for any finite n. So you only know it's going down to 0, but you don't know the rate, right? How fast does it go? In fact, the convergence in the CLT is not uniform in the underlying distributions of xi. So what does this mean? It means that it can be faster for some distribution depending on the original sample, like the distribution of xi or yi, the scale version. For some distribution, this convergence may happen faster than for other distributions. Okay, for any fixed sample size n, there are distributions for which the normal distribution approximation is arbitrarily poor. However, there's an upper bound. Okay, due to Berry and Essen, 1940s, to the error of the CLT approximation that shows the convergence is uniform for the class of distributions for which your yi, okay, the scaled version has a finite third moment. Okay, absolute value third moment. So essentially, you need your original sample to be not so heavy-tailed to have the convergence fast. Otherwise, the convergence is not so fast, which actually makes sense, right, intuitively. So this is the Berry-Essen theorem. There exists a constant C such that y1, y2, and so on are IID random variables with mean 0 and variance 1. Then the sup of the difference between the actual CDF function of Tn, right? Tn is the scaled root n times yn bar, and the limiting CDF, standard normal CDF, their difference is upper bounded by this thing. Okay, C is a constant. This third moment depends on the original sample's distribution and root n. So essentially, if you have the original sample's third moment being finite, right, then this, this sup difference goes down at the rate of 1 over root n. So you know this. And for all n, that's it. So in the original SAM sequence, x1 to x2 and so on, if we define the moment, the unscaled third moment, center moment to be this rho, then essentially, since yi is xi minus mu divided by sigma, sigma will enter here, right? Become sigma cube. And so essentially, it will be this form. So this is just the unscaled version. This is the scale version expressed by ym. Yeah. Okay, so we can just finish this part of discussion. We will not give a proof here. Instead, readers can refer to these previous papers that show the proof. And the former authors gave a proof of the theorem based on the Stein paper that gave the value C 6.5. However, they did not prove that 6.5 is the smallest possible value of C. And in fact, an interesting aspect of Berry-Essen theorem is that the smallest possible value is not yet known. It's a constant. So for example, at that time, when Y prepared for this class, C was reduced to this 0.747 already. So you can see 1/2. And furthermore, Essen himself proved that C cannot be less than 0.4097. So you already have a very small interval between this. And for the sake of simplicity, people typically take C to be 1/2. Yeah, so essentially this is the upper bound you actually get for this difference. All right, so essentially it's about using the CDF function of your error, your root n times error, how well can that be approximated by standard normal distribution in the CLT case? Okay, so let's continue with our discussion on Bootstrap, coming back here. So now you see what is Berry-Essen. It's a upper bound on the sup x difference between two CDF functions. Example 7, suppose that x1 to xn following f distribution with mean mu and variance sigma squared. Suppose we want to construct a confidence interval for mu. Let mu and hat be the sample mean and define the error distribution, right? So we also follow that notation GNX, which is our GN at T, at T for the CDF. We call this our performance measure, lambda and F. So essentially, it's defined as the probability that root n times mu and hat minus mu is less or equal than T. Okay, so then to do the Bootstrap plugin estimator, we consider a hypothetical sample x1 to x1 star to xn star from f and hat. And then based on this hypothetical sample, the hypothetical estimator becomes mu and hat star. So then to do the plugin estimator for G and T, everything with a hat added, right? G and T becomes G and hat T. F is changed to F and hat. Here in the probability, F is changed to F and hat, and the estimator mu and hat becomes the hypothetical one, mu and hat star. The parameter mu becomes mu and hat, right? Everything follows. So now you're interested in how well does Bootstrap plugin estimator G and hat n estimates the GNT, right? And this is so-called Bootstrap theorem. What it says is, if your original sample has finite third center moment, mu3 being finite, then the sup difference between the two CDFs, one is the plugin estimator, one is the thing you're interested in, empirical, the error distribution CDF, they are bounded, and they're upper bounded by this order, 1 over root n. So it's the same order as in the Berry-Essen theorem, right? 1 over root n. So how can we actually show this? Essentially, you just need Berry-Essen to help you do this. So we just saw this. Berry-Essen theorem says let x1 to xn be IID with mean mu and sigma squared. Let this mu3 be the center third moment of xi, and zn be the standard version and also multiply by root n. So basically the average, right? And then phi is the CDF. Then essentially the CDF of zn and the standard normal CDF, their sup difference is upper bounded by this. This is what we just saw that. Okay, now to prove this Bootstrap theorem, we need to decompose the left-hand side the sup difference in the following ways. Okay, so first of all, let phi sigma t denote the CDF of the normal distribution with standard deviation sigma. Let sigma hat n squared be the sample variance. Okay, sample n variance with dividing n variance. Then sigma hat squared is actually what? Is actually the variance of this error. So essentially, we are multiplying root n to this hypothetical sample mean. We're talking about the sample mean estimation problems. Hypothetical sample mean minus the actual sample mean, root n. And we can show that this is exactly this sigma hat n. Now, by the triangle inequality, we can actually show what? Do the decomposition. So G and T minus G and hat T absolute value, we introduce this normal CDF. So we first compare the actual error distribution to the central limit theorem version CDF. And then for the central limit theorem version, we compare to the plugin version. The plugin version uses sigma and hat instead of the true sigma, okay, based on our sample. Finally, we compare the plugin, which is based on our sample, to the normal distribution with sigma m. So you see, the idea is that for the first term and the third term, we can apply Berry-Essen. And for the middle term, we can just show that based on the property of sigma n hat, how close is it to sigma, we can make sure that the two CDF, normal CDF functions are close. That's basically the idea. Okay, so yes, first term A term is comparing the error distribution we want to have, and it's limiting, right, the normal distribution based on CLT. And for this one, we are just directly applying Berry-Essen, nothing much. And third term, same argument based on Berry-Essen. And now the middle term, the middle term here is based on Taylor expansion on the CDF function of normal. So expanding that around sigma, and then you can get a term which is the difference between sigma hat n and sigma. Yeah, that's it. Okay, so essentially, we are showing this because using Berry-Essen as the intermediate, we can connect these two things using the central limit theorem's error bound as the intermediate. That's basically it. So I think maybe this diagram can provide a better summary. The idea behind this proof can be summarized and illustrated by the following diagram. So GN, error distribution, is close to the central limit theorem normal distribution by Berry-Essen in this, right? And their difference is fixed, it's not random. And this, they just differ by the sigma, whether it's the true standard deviation or the estimator version. And that they are different by OP, 1 over root n. This is because this sigma hat n is an estimator of sigma with this error 1 over root n. And big OP here because this is random. So whenever it's random, we need to use OP instead of O. And then these two things both depend on the random standard error. Their difference is big OP. Then the question we want to ask is this question mark, how far away they are from each other. And based on the proof, we say this is big OP 1 over root n. Okay. And for the approximation using Bootstrap, since we said that we cannot get a plugin estimator exactly, we get the Bootstrap version. So we approximate that using Monte Carlo, and that error itself just depends on B. So when you set B to be large, then they're very close to each other. Okay. Okay, so now let's look at one example to help us understand this better. It's called performance of a classical plugin versus Bootstrap estimators for variance. Now let's look at two versions of estimators for variance. Let x1 to xn be IID with mean mu again, and TF, which is the parameter of our interest, is said to be the variance or second moment, right? This is the parameter of interest, and we assume there's a finite fourth moment. Okay. So the plugin estimator for the variance, we can denote it by TF and hat. So we write M2 instead of mu2, mu for the population version, M for the sample version. So essentially, this is the sample variance, right, plugin, which is exactly following the plugin or the V estimator. Essentially, we consider each xi to be one value, and the probability mass is 1 over n. So by the definition of variance, this is exactly the variance on our sample, f and hat. All right, then the performance measure, we define that to be the variance of the estimator scale inflated multiplied by root n. So we stabilize the variance. And we can show that the exact variance or performance measure is this. It involves n, since our sample version, sample estimator depends on n. But here mu4 is the population fourth moment, mu2 is the population second moment. Okay, and as we said, for many cases, the performance measure may have a limit as n goes to infinity. And this is it. So lambda and f, by letting n go to infinity, you can see what? It's just the first term. It's just this term that stays because these terms will go down to 0. So this is the lambda f. just the fourth moment minus the second moment squared. Okay, so what is the classical estimator in this case? The classical estimator is that you directly plug in into the limit. You do the plug-in for the limiting performance measure instead of estimating the performance measure for finite m. So in this case, you're using so limiting version, you see, only has this term remaining and this term gone, right? So when you do plug-in, you just plug in this one. So you change mu4 to m4, you change mu2 to m2. That's it. And m4 is the sample fourth moment. Okay, that's it. This is when we call this classical estimator lambda fn. Pay attention to this because it's lambda, not lambda m, because we're using the limiting limit, which no longer depends on n and only replace f by fn hat. We're not estimating lambda nf because here the performance depends on n. This is a key thing to note. Okay. However, the Bootstrap estimator, look at here. The Bootstrap estimator is trying to plug in lambda nf, not lambda f. So essentially, here's lambda nf and hat. So when you do plug in, you keep all three terms above. You plug in each. Mu4 becomes m4, mu2 becomes m2, mu4. Yes, you see, each of the three terms remain. Just we change mu to m. Does that make sense? So therefore, you have two estimators. This is estimator 1, and this is estimator 2. Okay. And this one only keeps the first term of this one. But in both estimators, the dominating term is the same. Okay, it's this one. You have the same dominating term. But their difference is in this term. Okay. And using either estimator, if you compare the estimator to the performance measure of your interest, which is lambda nf, you take the difference between this and this, difference between this and this. You still have the same dominating term here. And the remaining terms are just in the order of 1 over n, right? Okay, so from lecture 11, we showed that this one, so mk minus mu k, sample moment minus propagation moment, always have a limited normal distribution using the delta method. Remember that. We also use that to derive the asymptotic normality for the sample correlation. Remember that, right? So now you see that in this case, because we know this stabilizes with the limiting distribution, so we can say that the error itself is in the order of 1 over root n, right? Because we multiply that by root n, then we get a stabilized distribution. So therefore, we can say this term, dominating term, has the order 1 over root n. And the difference between the two estimators is in the order of 1 over n. So, yeah. So I'm just showing that this explains that the Bootstrap estimator actually captures or try to do more plugins into the smaller terms, while for the classical estimator would directly plug in into the limit of the performance measure. Okay, another example. In this example, our performance measure is the bias. So suppose that we are still interested in the parameter sigma square variance, and we're using the sample second moment as the estimator, right? And we know the sample estimator 1 over n dividing n is biased. So in this case, you can see that this is the expectation of the moment, which is not exactly sigma squared, but it's sigma squared times n minus 1 over n. So it's not 1, right? So we have this bias. So therefore, you see the bias, finite sample bias is exactly sigma squared over n. And of course, we know this bias will go down to 0 as n goes to infinity, right? So what do we do? If you are just using a classical estimator, then it's zero. That means the bias, you just estimate to be zero because you know that asymptotically the performance measure bias going down to zero. So you can just say, okay, I estimate the bias to be zero. And here in this case, using zero as an estimator for the finite performance, you know the error is 1 over n. They differ by that. But if you use Bootstrap estimator, you will plug in. You'll plug in sigma squared by m2 squared, right? And doing that, you know m2 squared is itself sigma squared plus OP1 over root m because they differ by 1 over root m. So then together, you can see that this Bootstrap estimator minus this actual performance measure, their difference is actually in the order of 1 over n to the power 3 over 2. It's not 1 over n. So that's why in this case, the Bootstrap estimator provides a better approximation for the bias than just using the classical estimator. Because classical estimator, you would just straightforwardly estimating at zero, bias at zero. But here you will not estimate bias at zero, but you're using Bootstrap to provide estimator. Yeah, so actually there's a theoretical study showing that Bootstrap is advantageous compared to classical estimator when the performance measure has a limit that does not depend on the distribution. So in this case here, we have the limit at zero, right? Zero doesn't depend on the original distribution. So that's why Bootstrap here is better. So in the previous example, Bootstrap and the classical estimator, the two estimators have the same error rate, but this one, Bootstrap has a faster error rate. Does that make sense to you? Yeah. So basically the intuition is that if the performance measure is convergent to a limit that doesn't depend on distribution, then using the classical estimator, you would just use that limit, a constant, as your estimator, but that ignores the f because it doesn't depend on f. However, using Bootstrap, you are not estimating the limit. You're not plugging the limit. You're plugging lambda and f. So in that case, you still capture some of the data's characteristics about the f. Yeah. Okay, let's look at the remarks. Remark 1. The Bootstrap is concerned with the estimation of functionals lambda and f that depend on n as well as f, n and f, while the classical estimator only concerns lambda f, the limiting of lambda and f. This situation arises in particular when lambda and f measures the performance of an estimator, okay? And they cut theta hat n. Remark 2. The Bootstrap estimator lambda and f and hat can be represented as a function of the actual sample x1 to xn. This is because f and hat depends on the actual sample. From f and the conceptual sample, or we'll say hypothetical sample x1 star to xn star from f and hat, right? They are sample with replacement from x1 to xn. This representation shows that except for very small n, the calculation of lambda and f and hat often requires a prohibitive amount of labor enumeration, right, of all the possible sample with replacement. The difficulty can be overcome by approximating lambda and f and hat by means of Bootstrap samples, xi1 star to xin star, I goes from 1 to b. The resulting approximating converges in probability to lambda and f and hat as b goes to infinity. This is something we said, right? Stage 2, Monte Carlo approximation. Remark 3, consistency of lambda and f and hat as an estimator of lambda and f is less routine and more difficult to prove than consistency of classical estimators. Yeah, because classical estimators just deal with lambda f, the limit. Remark 4, when lambda and f with lambda independent of f, the Bootstrap estimator typically provides a better approximation to lambda and f than does the limit value lambda. So that's the thing we said, right? When the asymptotic bias is zero, it doesn't depend on f. It's just its constant lambda. In this case, Bootstrap does better. But this result can no longer be expected when the limit lambda f of lambda and f depends on f, right? So that's the thing. Okay, some counter examples to the Bootstrap, where Bootstrap fails. Okay, I think this is very interesting to know, and we will wrap up our today's class by finishing this counter example. Extreme order statistic. This is something we already covered. Suppose x1 to xn IIDF, and f is the CDF of uniform 0 to theta, right? This is what we talked before. We're interested in estimating this upper boundary, theta. Let TF to be theta, being theta denote the upper bound of the support of f. A natural estimator of TF is the maximum order statistics xn. Consider the performance measure. Lambda nf equals to this thing. Remember, we talked about this, right? Upper bound minus xn times n. And that is the statistic that has a limiting distribution, essentially. And we showed previously that this will converge to an exponential distribution. We showed that, yeah. Okay. And in this case, this is converging lambda nf as a CDF function at A will converge to the exponential function CDF function at A. Okay, now consider the Bootstrap performance measure. So for Bootstrap, you are now going to plug in this, all right? So essentially, the upper bound theta becomes sample upper bound xn, and this xn becomes xn star, a hypothetical thing. Now, under the empirical CDF, and now you can see that under this empirical CDF, this hypothetical upper bound is equal to the actual sample upper bound with this probability. This can be calculated just by assuming like it can be one of them with probability 1 over n, right? And then you just calculate the probability. So 1 minus this means that this, you calculate this to be equal to other things other than that, right? And so equal to other things is 1 over n minus 1. And if everyone is not taking the maximum, then that is this probability raised to the power n. So this means that all the hypothetical samples in this n hypothetical sample is not taking the actual maximum. That's this probability. And taking 1 minus that means at least one of them is maximum, right? So you see this thing happens with probability converging to this limit. And we know this, right? We know this 1 minus 1 over n to raised power n is converging to exponential minus 1. So therefore, you see that this limiting distribution, sorry, I should scroll down, n times their difference being less or equal than a, this thing is larger than the probability that this difference is exactly 0, because less or equal than a contains being exactly 0. And being exactly 0, we know is convergent to this limit as here. So essentially, you can see that I'm having a different limit. So I'm saying not different limit, I'm saying that if you take the Bootstrap plugin minus the performance measure, you take their difference, then you can calculate that they're here, and this is not equal to 0. Right, so basically it shows that in this case, if you're estimating the upper bound as the parameter, Bootstrap will break down. Yeah. So this is one very typical example where Bootstrap does not work well, where your parameter is not some, how to say, moment, population moment. It's not an average, but it's the upper bound. Yeah. Yeah. And this can actually be quite reasonable. Again, this is because your sample is only a discrete version of your distribution of uniform 0 to theta. And your sample maximum will never be exactly theta, right? And now you're using the hypothetical sample maximum, their difference from the sample maximum, because the hypothetical sample is still sample from the same sample. So then their difference can be still discrete, right? Depending on whether you captured the maximum sample maximum in your hypothetical sample. If you do, then the difference is 0. If not, it's not 0. And this is not mimicking the distribution here, the uniform one. Yeah, I would say that is the intuition here. But just keep in mind that when Bootstrap does not work is when your parameter of interest is a boundary. Yeah, Okay, so that's why for extreme order statistic or extreme, yeah, for values that are kind of like the extreme of your domain, for these kind of things, you need a separate paradigm, right? Like the central limit theorem type of thing does not work. Okay. All right, so I think I will stop here. So I think that basically wraps up our Bootstrap part. Yeah. Okay, I'll see you on Wednesday. Yeah. Thank you.